Hi, this is Dr. Rick Fletcher at the University of Idaho, and I want to present to you the first, what I call, content module, and this is for Chapter 8, so we may label it something like 8.1. It's a content module, and what I'll be doing is breaking down the chapter into individual learning objectives, and then I'll give you a little presentation on what each of these are. So this chapter is titled Modern Atomic Theory, and we start by showing you a picture of, it's a capture taken from a YouTube video. So I'm going to show you just the beginning of that YouTube video, and then I'll come back and we'll talk about this picture and what it really means. So let's just take a look at this YouTube video, and I'm going to cut that off now. What you're going to see is these piles of salts, and then methanol is poured over the top of that because it's a flammable liquid, and then the demonstrator catches this on fire, and you'll see the methanol burning then. Okay, so there you go. Now what I've done is capture that image, and then we'll go back and look at this. This is that demonstration as they burn, and what you see is each of those plates contains different salts, metal salts. The first one being barium, and then the second boron, strontium, calcium, lithium, sodium, copper, and potassium. And what I want you to focus on is that there are different colors that are coming from each of these. The colors that come out of atom as it's heated up is specific to that atom, and it's specific to that atom because of the way the electrons are arranged around in that atom. And that's what we're focusing on in this chapter. So the colors tell us the way the electrons arrange themselves around the nucleus. And this has been used for thousands of years to make fireworks. The Chinese started this thousands of years ago, and each of the different colors you'll see as a firework explodes is because it contains a different kind of atom or molecule, actually, a metal. And each of the metals give off a characteristic color. And I've listed just some of these. Red is strontium, orange is calcium, and you can go back in this video and look at those different colors that are in that still I gave you, and that's what's in each of these fireworks. Now the question is, where do they come from? And that's where we focus on what I want you to learn in this chapter. And so this is from the end of each chapter in your book. There's a list of these learning objectives, and in this particular content module, we're going to focus on section 8.1 and then this first objective. So at the end of it, you should be able to describe the relationships among the wavelengths of light, energy, and color. And that's what we'll focus on in this content module. So we're going to talk a little bit about light and what it is, and as I'm sure you've learned in other classes, is that when we see white light, it's really a continuous spectrum of light. If you pass it through a prism or off a grating, you can break it into the multiple colors, and that's why it's white, because it's actually all colors in the visible part of the spectrum, which we'll talk about in a minute, blended into one, and we perceive that as white light. Well, what light is electromagnetic energy, and we're going to talk about what that means specifically in a moment. But let's just store that away. It is electromagnetic energy, and all light in a vacuum travels at a set speed, 3 × 10 to the 10th centimeters per second. And what that means is if I am in a fixed place, I am sitting in my chair, light is actually traveling past me. It is moving past me at a very, very fast speed. But you've seen this. If you turn on a flashlight, you actually can see there's a delay. If it's bright enough light, use a laser. There's a delay in the time it takes to strike another object. Now, usually short distances, we don't perceive that very well, but that's what's going on. There's actually a delay because it travels at a speed. So I want you to put that image in your mind. I'm going to sit in a position, and light is going to be traveling past me. Now, what we're going to focus on is the properties of light. That's the first learning objective in this chapter. So I mentioned that light is an electromagnetic radiation, and I've tried to show what that means in this picture. So there is an oscillating electric field. That's the electric part of this, and that just means when I talk about this to my student, I usually put a positive at the top part of that. So up here, I would put a positive, and down here, I'd put a negative. So I talk to them about putting a plate with a battery, and I'm then flipping that battery back and forth. So the plus side of the field is on the top plate, the negative part or the ground part is on the bottom part of the plate, and then what happens is it quickly flips over, and that's what's shown here as it's oscillating. So there's an electric field that is increasing in magnitude, decreasing in magnitude, and reversing its polarity as it's going through. Now, perpendicular to that, a part of it that we don't talk about very often is that there's a magnetic field, and that plays a role in chemistry as well, but that plays a role in what goes on in the nucleus. And it's actually the electric field that interacts with atoms and its electrons, and that's what we're focused on in this chapter. So we're going to talk about the electric part of the electromagnetic field, which is what light is. So the properties that I want you to be familiar with, it is electromagnetic radiation, and it has intensity, which we term amplitude. So that's how large that wave is, the amplitude of that wave. Now we characterize it by wavelength, and we give that symbol always the symbol lambda. And that's a Greek letter, and you have to be able to write a lambda because lambda always means wavelength. And that's true whether you're talking in chemistry or physics. It's a symbol that almost always comes to mean wavelength. And what it is the distance between two adjacent peaks. So I could, if I could freeze a light wave, I could measure peak to peak, and that would be the wavelength. There's also a frequency because, as I mentioned, it's a moving wave. So if I'm sitting in a position, and if I were quick enough, I could watch light go by. And first one of those peaks would go by me, and then another peak would go by me, and a third peak would go by me. And the rate at which those go by in peaks per second is the frequency. So already you can start to think about this. Well, if the wavelength is a long wavelength and the speed of light is constant, then the frequency that light goes by me, peak to peak, is going to slow down because it travels at a constant velocity, and therefore the time for one peak to go by me and another peak to go by me is going to be related to the wavelength. And we'll talk about that in a little bit more detail in a minute, but now let's just talk about the fact that there are these different wavelengths, and that is the energy range of light, and it goes actually from a high energy to a low energy. And I've shown that in a picture here where the wavelength is plotted along the top, or actually the wavelength is on the bottom of that scale. And as you can see, the higher numbers, larger numbers are to the right, so those will be longer wavelengths, and then shorter wavelengths on the left. And what you notice from this is that the high energy wavelengths are actually the high frequencies. So those are very short wavelengths. And those are things like gamma rays, X-rays, and ultraviolet light wavelengths. Those are the high energies. And then the longer wavelengths, and therefore the shorter or lower frequencies, are radio waves or microwaves, that sort of thing. So X-rays and gamma rays are higher energy. Ultraviolet light is a high energy. Infrared is a lower energy, and microwaves are lower yet. So now we want to focus on a smaller section of that entire electromagnetic spectrum, because I want to call it the visible part of that spectrum, because that's the portion of the spectrum that you're probably more familiar with because our eyes respond to those wavelengths. And I've shown that in this picture, that it's actually a fairly narrow range of wavelengths. But in fact, our bodies do respond to a wide range of wavelengths. And I've listed, for example, X-rays. You've seen X-rays. X-rays pass through our body, the soft part of our tissue, but are absorbed by the dense parts, say the bones, and so it shows up as contrast in an X-ray. So our bodies do interact with X-rays. Ultraviolet, if you go out in the sun and you get sunburned, that's because the ultraviolet light is damaging the molecules on your skin in certain ways. So again, our bodies do interact with a wide range. If you put your hand under an infrared lamp, you'll feel warmth. You won't burn, but you'll feel the warmth. But it's light of the 400 to 800 nanometer wavelength range is what we call the visible, because our eyes respond well to that wavelength. Now, some of you can see farther into the purple or indigo. Some can see less into the red. And you'll find out if you have a way to measure that certain people see certain colors better than others. But our eyes do respond to the visible light. And that's actually a pretty small portion of the light. But these other range exist, these other wavelengths exist, and you need to be aware that they are actually quite important. But just to summarize, so light has intensity, which we term amplitude. That's how big those waves are. But we characterize light by really two parameters, and that's wavelength and frequency. And those two parameters are it's important to understand they're inversely related. So if I am sitting in a chair watching light go by at a set speed, the longer the wavelength, the lower the frequency. So I sit and I watch a peak go by and then count the next peak and count the next peak. That depends on the wavelength of the light because it's traveling at a set speed. So they are related, and we can be quantitative about that relationship. And that's what I've tried to show here, that the energy of that wavelength is really equal to this thing we call Planck's constant times the frequency. But what's most important is you understand that the energy of the wavelength is proportional, and that's what Planck's constant is just a constant that is that proportionality constant times the frequency. So as the frequency of light increases, the energy of that light increases. And we relate that to the wavelength because they have an inverse relationship. So if we start with this basic expression that the speed of light, which is constant, is equal to the wavelength times the frequency, speed of light, c, is equal to the wavelength times the frequency. So as the wavelength gets larger, the frequency must get smaller. I can do a rearrangement there, just divide both sides by that wavelength, and that allows me to cancel it out. And you can see then that frequency can be written by the speed of light, c, divided by the wavelength. And then if I just substitute that, and what I want you to see here is just that the energy is then inversely proportional to the wavelength. So energy is directly proportional to frequency. That is, as it gets larger, the frequency increases, so will the energy. And as the wavelength gets larger, longer wavelengths, that means the energy of the wavelength goes down. So energy inversely proportional wavelength, directly proportional to frequency.